Well, now, hopefully you've made some attempt to do this. But let's go ahead and write out what we get. A times this is just 0.4a times, or 0.4 components are 0.4a and 3a. And here we have 0.7b, negative 1.5b, and 3 times the vector 3, 3 is the vector 9, 9. Make sure we see if that's a comma. That's starting to look like a J. You know what it means. Okay? So this translates immediately, just multiplying through by our numbers A and B, the symbols that represent our numbers A and B, we get this equation. Well, let's see what we can do here. If we add 2, well, the 0.4a means we move 0.4a in the x direction. The 0.7b means we move 0.7b in the x direction. So our net x movement will be 0.4a. Excuse me, plus 0.7b. Now what about the y direction? Well, we have 3a and negative 1.5b. So we have 3a minus 1.5b, and that should equal our vector 3v, which we know to be 9, 9. Okay, now do you see, if you haven't seen it before, you see how to find a and b? Well, maybe you do, maybe you don't. Let's see. Okay, so this represents the x displacement for this vector. And 9 is the x displacement for this vector, and the two vectors have to be the same, so they have to have the same x displacement. So now we know that 0.4a plus 0.7b, thought I'd written something down wrong there, I had to check it. 0.4a plus 0.7b has to equal 9. And the same y displacement implies that 3a minus 1.5b equals, well, the y displacement of this, which is 9. Now let's move this board over here. Well, now can you find a and b? Well, this is just a set of two simultaneous equations in two unknowns. And there are many ways to write out this solution, many ways to do the solution. Now, the ways we've developed to date in this course, we could either reduce the augmented matrix. Of course, we could do we could do multiples of equations and eliminate variables. And I'm talking and writing at the same time, and what I'm writing is not what I want to be writing. Okay, so we have 0.4, 0.7, 9. We have 3, negative 1.5, 9. And we can reduce that matrix. Alternatively, we could write the matrix equation. 0.4, 0.7, 3, negative 1.5, multiplied by the column vector AB equals the column vector 9, 9. And this is, of course, of the form AX equals B, where this B is a B vector, and this B down here is just a number. The B with the arrow over it has nothing to do with this B. But this is the familiar way we've written matrix equations. Okay? So that X equals A inverse times B. so that AB column vector equals the inverse of the 0.4, 0.7, 3, negative 1.5 matrix multiplied by the column vector 9, 9. Of course, we can reduce this matrix, and the procedures are in many ways equivalent, because how would we get the inverse matrix here? Well, we'd reduce this matrix augmented by the identity, or we just reduce this augmented matrix. Either way, we get a solution and we find out what A and B are. Now, I'm not going to burden you with the with watching me reduce the matrix. I'll just write down the reduction, and then we'll discuss it and see what this tells us geometrically about these vectors.